Okay, we'll start from the last point. I think you can remember we have started about the melting in the mantle, the topic. So we were discussing about how the mantle can be melted, right? One way is to increase the temperature, and the another way is to decrease the pressure. That is what we call the adiabatic upwelling, right? And then we discussed another possibility to reduce the melting point, right? Reduce the melting point means to reduce the solidus temperature. For that, we can add some water into the system that will lower the melting temperature. So what is adding water to the mantle? What does it mean? Because we know we cannot immediately add water into the mantle, right? But there is some other some other possibility where we can do this water addition to the mantle. Can you think of? I can't do anything without your feedback. That's the problem. But anyway, we'll continue. Please ask to check the audio settings next time. I don't know what has happened. Okay, anyway, subducting slabs brings a lot of water, right? How can these subducting slabs bring water to the mantle? In all the convergent margins, what happens is uh, the subduction zones are generated, and a lot of hydrous materials are being brought into the mantle. So that is how the water is added to the mantle, right? So in subduction zones, that means collision zones, we have a lot of water there, right? That means the stored water, and also this water, when the slab is driven down to the mantle conditions, this water get, the stored water get evaporated. No, sorry, not evaporated. They just get dehydrated from the materials. Okay. Dehydration means the minerals, hydrous minerals like mica, amphibole like minerals, they bring a lot of water, right? Their structure stores a lot of water there, and this water can be added into the system. Okay, so what happens is this water reduces the temperature, the solidus temperature, so that it can easily start melting at lower temperature, right? To melt, as we know, we need heating, but in the absence of heating means also increasing the temperature. But in the absence of heat, if you, sufficient heat, okay, if you try to lower the melting point, then at a lower temperature, maybe at a low amount of heat, the melting can start. So that is the phenomena behind this adding water into the mantle or adding volatiles into the mantle, right? That causes the mantle to start partial melting, right? This is not full melting or the complete melting. This is partial melting. Okay. So the concept of partial melting, we have to understand several phenomena, especially the concept of partial melting, and also the fractional crystallization, the difference between those two processes, because those two are the main activities happening at the depth, which determines the composition of the earth as well as the evolution of the earth. Okay, so partial melting, as we already discussed, it's the melting, but not the entire mantle. but from place to place, the mantle starts to make some melt out of the original composition. So definitely it will change the existing compositions where this partial melting is taking place. And fractional crystallization, which is mainly related with the melt cooling. Okay, as soon as the partial melting started, the melts might be just concentrated around the source region, or it can immediately be percolated out from the area, right? Whatever the process, the formed melt will start to cool gradually. If the temperature gradient is high enough, they can even immediately start crystallization of new minerals. Okay, so cooling of a melt means crystallization of new minerals. So that is the second process after partial melting. So these two processes are taking place almost say concurrently. Okay, that means while partial melting is taking place, another place, the melt which was immediately percolated before from the source will start to crystallize even, right? Provided that sufficient temperature gradient is there. Otherwise, the melt will ascend, and as soon as it finds cooler environments, whenever there is enough temperature gradient, a new mineral will appear. Okay, so it might take some time, or it can be happening very immediately. So those two things we have to understand, and the process is not very simple as we think. There are so many factors to be considered. We will gradually see what are the factors that we have to consider regarding partial melting and fractional crystallization. And then another important thing is there, that is elemental partitioning. Okay, so elemental partitioning means the exchange of elements between the residue and the melt. Okay, so we have a residue and we have a melt, right? So partial melting causes some melt to form, but it might not be at once formed. It may be gradually formed and then interconnected, like different melts from different sources can be interconnected, and then it can be transported upward, or it can be ascending to the shallow levels. And during this melt ascend even, right? I said that when the temperature gap is there, there can be new mineral crystallization. Okay, so new mineral crystallization means it will form a solid again, right? Some solid material is formed. So in the melt also, we have in that case a solid which is in contact with the liquid. Okay, so we have the liquid outside, and at the same time we have a solid also. So two phases are there, basically, solid phase and liquid phase. So in the case of partial melting, also what happens is, so we know gradually small melts will be generated. So at the same time, at the time where the melt is formed, you will have again the same two type of phases. Okay, so you have melt and solid in between, in contact. So there is possibility for elemental partitioning. Partitioning means the exchange of elements from solid to melt, or from melt to solid, like that. So this can happen in both the residue and the melt during partial melting as well as fractional crystallization. So during these two processes, elemental partitioning is happening. So this elemental partitioning to happen, there should be certain criteria to be accomplished also. Okay, so all the elements will not move here and there as they want. Okay, so other physical parameters are necessary to control them, for example pressure and temperature, and also the overall composition of the solid or the melt. That is the first requirement. And then there is another requirement which we call partition coefficients. Okay, so there is another factor that we have to consider, that is partition coefficients. So these partition coefficients are always associated with this elemental partitioning. Okay, to partition, these partition coefficients should be suitable between the two phases, right? So therefore, we have identified two types of partition coefficients, which are called intermineral partition coefficients and intramineral partition coefficients. So intermineral, you can easily understand when you have two minerals together, okay? In between those two minerals, partitioning. But intramineral means within a single mineral, okay? Inside a mineral also, there is possibility for this elemental partition, right? For example, zoning. Zoning is entirely dependent on this type of exchanges based on the partition coefficients. So even in the solid or even in the liquid, you have to consider these partition coefficients, right? So solid materials crystallized or the liquid formed in the system whenever there is two phases, right? So these partition coefficients matter. So it's very important. So we will learn about partition coefficients later separately. And the other concept that we must understand is regarding melting is the mechanisms of melting. There are three main types of melting, or three types of mechanisms of melting, which we call batch melting, fractional melting, and incremental melting. These are three types of major types of melting. There are other mixed type of melting also in the nature, but we will see first, actually at this level, undergraduate level, we have to understand these two melting mechanisms, batch melting and fractional melting. Sorry. This incremental melting might not be considering in this level because it's a little bit complicated compared to these two, right? So we will see gradually about these aspects. But before proceeding, you have to have some type of keywords, right? Partial melting, fractional crystallization, elemental partitioning, partition coefficients, batch melting, fractional melting, at least, right? So these should be like keywords during this whole course. Okay, these are very important. Okay, so as I said before, this all these melting processes are very complex. Okay, they are very complex in the sense the way the elements behave is unpredictable. Although we can generalize some kind of relationships considering their chemical behaviors determined by their relative positions in the periodic table. Okay, their relative positions in the periodic table is very important because that determines their chemical behaviors, because the similar behaviors, similar geochemical behaviors are shown by closely sitting elements. Not all, but several characteristic element sets are there, which are sitting close to each other. That means their atomic numbers are close by. They behave similarly. In most cases, in geochemical processes, in geological processes, and also their ratios. Especially trace element ratios are important, but not all the ratios we can use. Some identified ratios are there, and such ratios are also there to characterize different geochemical processes. For example, some trace elements as well as some trace element ratios can be used to determine whether a particular basalt or whether a particular melt or a magma is coming from mid-ocean ridge setting or island arc setting or OIB, oceanic island basalt type, like that. We can determine based on these behaviors. So, and also if for a magma, if it is mixed with another type of magmas or another type of sediments or some melt derived from crust or something like that, for such kind of complex situations, we can use these trace elements, some of the trace elements as well as some of the trace element ratios to characterize. So in that case, we use or we term them or we call them geochemical traces. These identified elements. So we will get into know of them during the course as we progress. And as I said, once the melt is formed, the nature of it or the nature of its composition entirely depend on the conditions prevailed during the formation. Okay, conditions prevailed during the formation of the melt. Right, so that is very important thing, because PT conditions as well as other surrounding environmental ambient factors within that melting region. That means, for example, oxygen fugacity. That is also very important. So oxygen fugacity, oxygen fugacity is how oxidized or how reduced the relevant area, right? If you have a lot of oxide phases, like opaque phases crystallize in there, that means it's an oxidizing environment. But if you have a lot of sulfides formed instead, then it's a reducing environment, right? So these things are very important to determine the formed melt composition or the magma composition. And also another thing, which is the reaction with the solids. The formed melt, right, usually start to react during the ascent, right? So partial melting was taking place, the the liquid formed, and this liquid goes out, and this is going out through the solid lithosphere or solid mantle, okay, upper part of the mantle, asthenosphere, and it can start reactions with these surrounding rocks. So that if reactions take place, then what happens is the coming out melt will be having a different composition, right? So that does not characterize the original composition that you expect for it to have, right? So original composition will be not as same as the second stage melt, because it has already reacted or has some modifications during these wall rock reactions or melt rock reactions. Okay, so that is another thing which makes more complicated situations for this mantle melting. because sometimes we can't predict, even we don't know how these reactions have taken place. In some situations there is no any reaction, the entire melt can be escaped without any reactions. All depend on the physical conditions prevailing there, redox conditions and all everything. Okay. And also the pressure temperature things, that is very important. And volatiles, the other thing is volatile. As I said before, or the presence of water. Okay, presence of water or volatiles that will make the melting temperature reduced. So in the course of this melt ascending, the initial melt, maybe if a more cooler environment is there in the upper levels, what happens is this part will also start to form a new melt, right? So the the initial melt and the second melt will get mixed here and come up as a entirely different melt. So that is also there as a possibility for mixing of different types of melts generated at different levels, different depths. So this is also affecting the outgoing melt compositions. So this type of complexities are there when we talk about the general melting in the mantle. But most of the cases in geochemistry, what we do is we generalize, and of course some assumptions we have to use. With those assumptions, we have to make a kind of a picture so that we can resolve some of the existing questions regarding the magma generation, magma formation. Okay, so I think we have to think why the mantle want to melt, right? So we say that for melting, either heating or pressure or pressure drop is necessary. So that means we are creating in the nature, naturally in the mantle region, some PT slopes. Okay, some PT gradients. PT slopes means PT gradients, and for the ascending bodies, that means the if as a result of this mantle convection, don't forget about mantle convection, okay, because that is the driving force. That without that nothing will happen. So this the mantle convection brings up unmelted materials upward, okay, because this is convectional current. I mean, these convection currents can bring materials, okay. You can easily visualize that when you boil a pot of water, and if you have put some drops of ink there, you will see this ink ink is also being floated. I mean, they are also taken up by the convecting current, convective heat currents, right? So that means convection has a possibility to move the material, transport of the material. The same thing is happening in the mantle also. So therefore, these ascending bodies, these upfilling bodies, ascending bodies means the hot material coming up towards shallow regions, we call upfilling, right? And these materials will hit with the mantle curve. That means the different the solidus temperatures, because depending on the PT levels, if they hit that curve, immediately that material or that ascending body can start partial melting. So that is the requirement. At least we have to hit the solidus by increasing temperature or decreasing pressure, as we already discussed before. So this happens because of that. Actually, this mantle melt is produced. So that is the reason for melting of the mantle. Otherwise, mantle will remain there as it is, right? So no magma, no volcanoes, nothing will be there. But this is naturally happening, and convection is always there. So that drives the plates. So plate tectonics is there. That means a lot of activities are taking place. So therefore, this melting will also happen from place to place within the mantle. Asthenospheric region, okay? Within the asthenosphere, in the lower mantle, you don't expect melting to take place because there are no much convective forces to bring up the materials. Unless you have a plume, mantle plume, which is coming from very deep in the from the core mantle boundary, and that can brings up more uh, um, unmelted materials, and with that high temperature, these materials can start melting, and also due to the heat flow, sudden heat flow, the shallow level mantle materials can also be melted. I mean, even within the lower mantle, right? If you consider the core mantle boundary, lower mantle is above that, so that means it is shallow. It's a kind of a shallow level with respect to the core mantle boundary level, right? Depth. But if you consider the upper mantle level, where the asthenospheric melting is usually taking place, like normal mid-ocean ridge basalts, that is very, very shallow. Okay, it's just for maybe 40, 50 kilometers even, right? Okay, so as we discussed before, we have melting types, right? Batch melting and fractional melting, mainly to consider. Okay, so we have this batch melting we call equilibrium batch melting. What happens there is the formed melt, the newly formed melt remains in contact with the residual crystals. So that means if you have the solid here, unmelted solid here, and as soon as the melting starts, some drops of melt will form there. Okay, so this melt remains in contact. It will not go out. It will remain there. So another place, maybe another drop of melt formed, another melt formed, like that. It will be kind of accumulation of drops of melts, and they remains in contact with the solid. Okay, the residue here, it is in contact with that for a certain period of time. Okay, so during that time, all these elemental partitioning and all can take place also. So finally, they will come to a equilibrium condition. This composition wise, I mean the elemental composition wise, right? Not the overall composition of the two phases. Okay, because elements can move depending on their properties, as I said, geochemical properties, and based on the partition coefficient. So that process is taking place. That is what we uh, consider equilibrium. Okay, and since nothing has gone out from the system, right, because still the melt is there, the solid is also there, elements are moving here and there, but within this particular system, right, nothing has gone out. So therefore the bulk composition of the system remains constant. Okay, so before melting we had one composition like this. Okay, so after melting you have the composition changed as solid and melt, but the system as a whole remains constant. So therefore there will be no change of the bulk chemistry of the system, as long as this system is considered, right? Because the melt is already there, remained within the system itself. It has not gone out from the system. So it is now there as a batch, okay? Because they were getting drop by drop accumulated, and that melt was generated, I mean, initial generated position places, the melt was just accumulating, and now it is like a batch there, right? So if at a certain time the melt will escape from the region, because it cannot remain there at very I mean, under changing physical conditions. So therefore at a certain point it has to remove out from the system. So then it will go out, but not as a single melt, but it will go out as a batch. It will go out as a batch, right? So that this melt will go out as a batch. So that is what we call the batch melting process, right? But initially, during the batch melting, the melt should remain in contact with the residual solids. Later, it will go out as a batch. And in the fractional melting, the other type of melting, it's entirely different. The melt leaves the system as soon as it was formed. Okay, so that means the unmelted solid is there. So as soon as the melt is generated there, it will just go out, right? So nothing will remain there to be in equilibrium with the solid. So in this case, actually single one drop cannot move as a melt, right? It will go out and concentrate or accumulate in fractures or some weak zones, and then it will make into a conduit and then go out as a melt conduit or melt pipe. Okay, so always you can't expect that the melt will remain with the solid, right? There may be some such situations, but majority of the melt is escaped from the system as soon as it is formed. That means each and every drop will go away from the system as soon as the melt was formed. Okay, so this fractional melting requires some melt pockets. Okay, some melt pockets. So I mentioned that they get accumulated somewhere outside the system. I mean, outside the source region. Let's say source region, and then they get interconnected. These pockets, maybe several pockets, maybe like this formed, and these pockets will be interconnected somehow later on as a single melt batch, right? Then it will go out as a big flow. So this is happening during the fractional melting. Okay. Anything you didn't understand? But I can't get your feedback. That's the problem. Okay, I hope you can get it well. Then we'll move to the next section. As we discussed before, effects of water is significant during this melting process, whatever the mechanism. I mean, batch melting or equilibrium melting, whatever. Because we know additional water lowers the melting temperature. Okay, so that will lower the melting temperature. So that means adding a little bit of water can lower the melting temperature significantly. So you can see, you can see here the original solidus was here, but it was moved to this level. That means a significant amount of temperature drop you could expect, right? So this is significant. So lowering this temperature allows the melting region with a kind of a flexibility, right? This kind of a flexibility zone to have melting taking place over a wide range, right? So during this melting process, over a wide range, this melting can take place. I mean, drops of melts can form at different intervals because when this water is added to the solid to the mantle, it doesn't add at once, right? Gradually, the water is added. I mean, the dehydration is taking place gradually. So initially, maybe a little bit of temperature drop is there. Then more than that, okay, and again maybe significantly greater, and finally maybe the entire region. So during this temperature change, at different stages, different melting can take place, right? So from 1 to say 2, 3, 4. Okay, 1, 2, 3, 4, 4. There can be different amounts of melt formed because the temperature drop is variable during this during this the time when these tectonic processes brings materials down into the mantle, dehydrating them. And also, adding this water, we can consider that it almost completely erase the effect of pressure on melt, because we had this solidus like that, and to start melting, what was needed, this one, right? The pressure drop or temperature increase, these two. But adding water made everything different, right? So maybe new solidus is like this. Okay, maybe new solidus is like that. So that means all the especially the pressure effect has entirely changed, because from here to here it's possible to melting to take place, because see, this level and this level is the solidus region where a huge pressure is required. If no water is there, huge pressure may be, I mean, difference may be necessary to reduce the pressure to make a melt at this level, right? From starting from there. But now we have reduced the temperature, solidus temperature, so that even without considering this pressure effect, I mean, we don't need any pressure change because the melting can be easily taken place from after adding this water. I mean, after changing this solidus temperature, right? So that means it completely erases the effect of pressure on the melt. Okay. And also there is possibility to decrease the amount of iron and magnesium which is going into the melt, right? Adding water. That is actually a different aspect we have to consider, but just keep in mind that hydration causes to reduce the iron and magnesium amounts which are dissolved into the melt. I'm not going to elaborate this one because this is a little bit complex matter, but just keep in mind that we talked about minerals which start melting first and then secondly this one, and thirdly that one, like that, right? Remember, the CPX is the first to start melting, right? We mentioned that before. Okay, so from CPX, iron can be gone out, magnesium can be gone out. So this is the concept. I mean, from phases, all these iron and magnesium is going out, right? So which decreases going out means if you wanted to heat this system without adding water, suppose you don't add the water, but instead you heat the system to produce the melt, then uh, the more you heat, the more CPX will go into the melt. That means a lot of iron and magnesium will go there. The next mineral start again then. So likewise, a lot of iron and magnesium will be contributing into the melt. But instead of heating, we stop heating, we don't do that, but we drop the temperature instead. Then this artificial melting of these phases will stop, but still some melt is produced from not only from CPX, but other melts, other minerals will also contribute. So there will be preferential contribution of iron and magnesium into the melt. So therefore, we don't see much. I mean, the rate. I mean, the increased rate we will not see in such kind of a situation during adding water, right? No intense amount of iron and magnesium will be added into the melt because we are dropping the temperature so that other minerals will also contribute, not from a single mineral, right? So that will cause the amount of iron and magnesium dissolved uh, in the melt, because other minerals will contribute other elements also, right? Not only iron and magnesium, calcium, and other elements also. So that means if you are adding more component into the system, means you are decreasing the concentration of these elements. Okay, you are decreasing the overall concentration of these elements. If only iron and magnesium there, it's entirely rich in iron and magnesium. But if you are putting more materials there, their relative the iron and magnesium's relative concentration will go down, right? So that is what is meant there in general, right? So just keep in mind like that. So this type of effects will have when we add water into the mantle melting, right? So this is determined mainly by subducting slabs or subducting materials, sediments, and the what the hydrous minerals going down. Okay. So these are very, very important principles you have to keep in mind considering the mantle melting. Okay, some important points we have to note down. So the melts are not always batches from mantle, resulting from temperature and resulting from one temperature and one depth. Okay, at different temperatures, at different depths, there will be some melts, components produced. They might not necessarily be batches. Batch melting causes to produce some batches of melts, but still these batches of melts can be generated at different levels, different temperature conditions. So therefore, this is an important point there. And another important point is the melt freezes as it rises. Okay, and not only that, that causes crystallizing other minerals. Okay, because as it rises means you are decreasing the both pressure and temperature, right, compared to its source region, right? Source region is here and the ascending melt is there. So here you get reduced pressure and temperature conditions, because the melt is moving towards shallow levels, towards upper levels within the mantle itself. So in other words, it indicates cooling, right? Drop of temperature means cooling. So this cooling should associate essentially crystallization of other minerals, because any melt, if you want to crystallize minerals from a melt, you have to cool it, right? If you want to uh, produce a melt, you have to heat. At the same time, if you want to produce solid out of a melt, then you have to cool it, right? You know that even in the kitchen, you are making a lot of food, right? Sweets. You heat sugar, then you produce a melt. But if you want to make sugar again, you have to cool it. The liquid you have to cool like that. And also, we need to note that the melt assimilates the mantle around it. What is assimilation? What is assimilation? Actually, it is not in equilibrium, because we can't expect always this melt to be in equilibrium throughout the pathway, right? Throughout the pathway of that melt, you can't expect that this melt will be in equilibrium with the mantle surrounding. Okay, so if it is not in equilibrium, means it will definitely start some reactions. It will start some reactions. So always the point is that melt temperature is above the solidus. That means that it is always as a melt. If it is at the solidus temperature, then definitely there will be no melt, right? The melt will be a solid. So as long as it is above the solidus, there is possibility which can react with the ambient solid mantle or the solid rocks. So that we in general call assimilation, right? Assimilation of the melt. And this assimilation causes again crystallization of materials. Because of this solid rock, melt rock interaction, some separate solid phases like other minerals can be crystallized. So that is another thing to consider, right? Not just melt, cooling, and crystallizes, but because of assimilation also there is a crystallization process taking place. So two crystallization processes can be taken place during this melt ascent. So overall important conclusion is the melt composition does not equal the basalt composition always. Okay, so what do you mean by this melt composition and basalt composition? Maybe it's a little bit confusing to you. Basalt composition means the first melt produced from the mantle melting. We assume that it is a basalt. Okay, if it is not reacted with the ambient environment and it was not modified, it will come up to the surface as a basalt itself, right? Mid-ocean rig basalts, for example, it comes out as a basalt itself. But most of the cases, apart from mob settings, apart from mid-ocean ridge settings, all other melts formed, maybe originally they are basalt, but later on, because of these above discussed changes, geochemical changes, the processes, affected processes, this melt will be not a basaltic composition, right? It may even be a granite at the end, right? It starts with the basalt, but finally it will come to the surface as a granite. Okay, it might be, right? Such possibilities can also be there. So originally it is totally mafic, but finally it's totally felsic, right? So this type of lot of changes can happen, and that is the important. Why we study about these trace elements and trace element ratios is to understand this type of different processes taking place within the Earth's interior, because we never know what has happened down there. So why we study, or why we are interested in trace elements then? Hmm? Can you think why we are interested in trace elements there? Why don't we consider these major elements? You know the major elements and trace elements difference, right? As the name suggests, major elements means the elements which are present in major amounts, in large amounts. Okay, trace elements are those present in in a material in very little amounts, very low amounts. Okay, so if you consider iron, magnesium, calcium, titanium, aluminium, silicon like elements, we always consider them as major elements. Okay, because you can find them in quantities greater than 1 weight%. They are always there in rocks greater than 1 weight%. Okay, 1 weight%, greater than 1 weight%. That means yeah, you can forget this weight term, but we use weight term there. It's more than 1% anyway, right? If you take the composition, total composition, minimum 1% will be there, right? But remember, we use it in geochemistry as weight percents. So 1 weight% is equal. Okay, I will tell that later. Then the trace elements, then the opposite should be less than, always less than 1 weight%, right? That means they are in very little amounts. So that's why we always use the term ppm, I mean the unit, ppm or ppb, right? Parts per million or parts per billion, because they are in very low amounts. You can't make it in percentages. If you want to make it in percentages, you have to mention 0.0 something like that, right? So 1 weight% is equal to 10,000 ppm. Remember, 10,000 ppm is equal to 1 weight%, right? You can see the weight, the unit conversions later, right? So these trace elements are present in very low amounts. But if you say this type of geochemical kind of modification has happened, right, during the ascent of a melt. So you have melt, original melt here. Okay, let's say here, original melt here, and the modified melt. Let's take we have modified melt. So if you measure the major elements there, right, original melt will have iron, magnesium, some few weight percentages, and if you measure this one, will also have some weight percentage. So the change, the relative change, if you want to show, may be very slight, right? You can't even detect. I mean, significant change cannot be discovered, because both are present in large amounts. So any change will not. We can't feel. For example, in this class, if there are 300 students, right? Maybe one or two students feel boring this lecture, okay, and maybe they are just escaping from the back door, right? Can I notice? I cannot notice easily, right? Because there are another 298 people there, right? But now you are few here, right? If one or two escapes there, I can easily find. So the change is very prominent in such cases. So if anything is found in very low amounts, and if you change its content, you can easily detect it. Okay, the sensitivity is high. So therefore, the change appeared in trace element changes, or the behavior, the trace element behavior is very sensitive in geochemistry. So that's why we take these trace elements into consideration very much. Okay, sorry, there was an interruption. I hope you can see the slides. Okay, if not, please let me know, right? By message or something. Okay. So that's why we are learning about trace elements, and we are considering about trace elements in geochemical behaviors. Okay, the change, the sensitivity is too high because they are present in very little amount. So that's why we are talking about anomalies. Okay, geochemical anomalies. We are considering geochemical anomalies because you can detect this type of changes very easily, right? If you consider the major elements, maybe very minor changes like that you will see, but nothing significant. But for trace elements, you will have this type of big changes up and down, right? Those are called the geochemical anomalies. When we plot in diagrams, we'll see. Uh, that's the reason. Okay. So these are important points. Okay. Do you have any questions? If you have any question, you can just type in the chat box. All right. So we will move to the next part that is also important. So we have been talking about the importance of major and trace elements during mantle melting. So now we have to consider what elements and the groups of elements we are considering under this igneous petrology, especially with respect to these melting processes. Okay, so I'm showing you the periodic table again. So this is nothing new for you, but you can see here the geochemical classification of periodic table. The geochemical classification of the table, you can see here. See, you have the first and second groups, alkaline elements, right? And then you have the first series of transition elements, and then below you have rare earth elements, right? So we have this one, alkaline elements and rare earth elements, and then we have another group we call high field strength elements. So remember these zirconium, niobium, hafnium, tantalum. Actually, we take them as couples like here. Zirconium, hafnium, niobium, tantalum. Okay. These are called high field strength elements. We'll see why they are called like that. And then we have another group here we call platinum group elements. So this group is named after platinum because it's including platinum. There you can see here osmium, iridium, platinum. Gold is also here, but sometimes we eliminate gold from there, but just let it be. Ruthenium, rhodium, and palladium. These elements we call, maybe you know already, inert metals. Inert metals. You know inert metals in the periodic table. You know inert gases here, right? Inert gases are there. Well, why do we call them inert gases? They don't react, right? So similarly, we have inert metals, or in other words, we call noble metals. They are we call noble gases, right? Or noble metals. That means they do not react with other elements. For example, you can easily remember the gold, right? So you are wearing gold on the neck or in the ear or everywhere, right? Uh, they don't react with anything, right? uh, I mean, they don't get trusted, right? Not like iron or something, right? They get trusted easily. Even aluminum get reacts with oxygen easily, right? Not only oxygen, other other agents also. So this particular group is called platinum group elements, and they have different geochemical behavior. And the transition metals, as you know already, they have their own behaviors. And then we have the rare earth elements or the lanthanide series. This is very, very important because we have to consider their behavior in geochemical processes, because there are identified or kind of textbook type patterns in these rare earth elements, which we can compare when we analyze the samples from different types of mantle melts. Okay, so if we compare them and to match with different tectonic settings, right, identified types of patterns are there, right? So therefore these are very important. Okay, so you can see here, previously I talked about weight percent, just one weight percent, and then you see here 1000 ppm, that is 0.1 weight percent. Okay, right, 10,000 means 1 weight percent. Right, so you can see the other all the types of elements with this category. Just get used to it. At the A levels, maybe you didn't consider all these elements, but in those who did chemistry at the first year, you must have learned about these different categories, but maybe not this geochemical classification, right? This is geochemical classification, these separate groups. So their similar chemical properties were taken into consideration in categorizing these elements into groups. So in other words, they are expected, right? They are expected to show similar geochemical behavior in geological processes, right? So we are expecting they will show some similar geochemical behaviors based on their chemical properties in geological processes. Actually, now you know, for many decades, right, geochemistry has evolved and people have identified their behaviors very well. So that expected behavior, I mean, the behavior we have identified can be used to predict uh, the possibilities when it comes to different geological processes during mantle melting, magma mixing, or whatever. But you know, we are getting a rock sample, right? For everything, for doing these all these things, we are getting a rock sample, right? We have to take that particular rock sample and do a geochemical analysis on that, right? Based on that, we get some results, and then we have to compare with these identified geochemical patterns. So for that, it's very, very important to select the right rock sample. Okay, the correct or the representative, the well represented rock should be collected. So therefore sampling is very, very important in all these geochemical determinations. Otherwise there is no meaning of whatever the facilities we are using. I mean, there are high-end machines, but if you are using I mean, a sample which cannot be, I mean, which is not representing the real rock that you want to analyze, there will be no use, right? Therefore, sampling at the very beginning, when you do field sampling, it's very important. And then you have to understand the petrology, the mineral chemistry and petrology under the polarizing microscope first of all, right? That is the real record of the rock, to eliminate some unwanted portions of the sample, or the unrelated reactions, or some other unwanted areas to eliminate, you must do preliminary investigation. After that only you can do this geochemical analysis. Otherwise, you are just putting some materials into machines and get some values, some numbers, and try to do nonsense. Okay, so it's very, very important. Okay, right. Now, this trace element categories, we as we said before, they behave in different ways, but some closely lying elements. For example, this. Okay, let me show you. Okay, rubidium, strontium here, right? They are lying close to each other, right? They are sitting close to each other in the periodic table. And barium, cesium, like this is just one example only, right? Some trace elements. Yeah, there are several such such groups. I mean, the couples, right? Even in trace in rare earth elements, you can consider ytterbium, lutetium, right? Lanthanum is there. Where is lanthanum? Okay, lanthanum, yeah, here. This is lanthanum, and this should fit from there onwards. Okay, so lanthanum, cerium can be used again as a pair also. So likewise, these closely sitting elements will give you some implications that can be used effectively, but not all the closely lying elements also, right? So there are some identified elements and also some ratios relevant to that. Okay. So we will move to the next part, that is entirely based on this the periodic table. Okay, so we determine a kind of a preference. We determine a kind of a preference whether some elements like solid phase or they like the liquid phase. Okay, so that preference is very important because I think we talked about some partitioning before. Okay, yeah, elemental partitioning. Here we talked about elemental partitioning. So this partitioning means the element behavior, I mean exchanges between solid and I'll put L for the melt, liquid, right? So if the melting region is here, some elements might like to go into the melt or the liquid, whereas some elements would like to incorporate into the solid. Okay, so depending on that, whatever the resulting composition will be determined. So for that, this partitioning is important. So for that purpose, we have to consider their preference based on their partition, something called a property or whatever, a calculated property called partition coefficient. Right, we will come into that later, the partition coefficients. But just remember this preference. This preference means whether they are partitioned easily into solid or partitions easily into the liquid. Okay, so melt or solid during the melting. So if some elements like solid phases much, then we call that element a compatible element. If some elements like melt phases rather than solid phases to go, we call it incompatible element, right? So compatible and incompatible elements means based on their preference to be incorporated into which phase, whether melt phase or solid phase. because before melting, right, we call fertile mantle, for example. Before the mantle melting, the region of the mantle part you can call fertile mantle, right? Any sample, in for example, if you are taking this portion of the mantle before melting, then it's you can consider it as fertile mantle. And later, either whatever the mechanism, either heating or dropping pressure or adding water, whatever causes melting, then you produce a melt as well as some residue. Okay, two phases will be produced. So during this formation of these two phases, some elements would like to move into this melt and escape, right? Some elements would like to remain in this solid itself, right? That is what we differentiated here as compatible and incompatible elements. Okay, so here you see a melt component is produced, a residue is produced, right? So some elements which like which are more for sort of partitioning into, sorry, what is happening? Okay, partitioning into melt. This is we call incompatible element, right? Here, if the some elements which are lying or which has the preference to be residing in the residual part, then it's a compatible element, right? Well, this is controlled, actually mainly controlled, but it doesn't mean that all the compatibles will remain in the residue, right? It doesn't mean something like that, just a preference only. But still there is possibility for these compatible elements also going into the melt. That is possible, right? But not much, right? Relative to the incompatible elements, a little amount of compatible elements will be going into the melt because they will remain in the in the mantle mainly because of their compatibility, a property called compatibility. We'll discuss these things later in detail. Okay, so the incompatible elements, that means the elements which has the preference to be incorporated into the melt, can be divided into two groups. Okay, two groups we call high field strength elements and low field strength elements. High field strength elements and low field strength elements. Actually, this division is based on their charge, their valency, the charge amount, and their size of the ionic radii. So this is collectively termed as ionic potential also, right? Based on this ionic potential, we divide them into two groups: high field strength elements and low field strength elements. These are very preliminary type of classification because you need to know these things. Otherwise, when we directly use them, you might get confused. Okay, so just keep in mind about these things. Don't forget to sign the attendance sheet. I will check at the end of the lecture series about your attendances. Okay, so therefore it's very, very important you sign the attendance, right? Don't sign for others if anybody is not attending the class. Okay, so high field strength elements means small but highly charged. What do you mean by that? Small, highly charged. That means they are small in size. That means their ionic radius is small, but their valence is high. They are highly charged. So usually we take the number ionic potential. That means this ratio, charge to size ratio, greater than 2. Okay. If that means if you divide their charge, their valency into, divided by the size, then you will, if you get a number greater than 2, you call it high field strength elements. So some examples are here, right? Zircon, hafnium, niobium, tantalum, right? Remember in the previous diagram, in the previous, here, sorry. Here, we categorize them into groups here. High field strength elements, right? So zirconium, hafnium, niobium, tantalum, right? So that is because of their ionic potential. And those which are giving less than 2 numbers, right? You can call them low field strength elements, or large but low charge. They are large, big, but their charge is small, because this charge, if it is big, then you are definitely getting a small value for this ratio, right? So that's why. So for example, cesium, rubidium, barium like elements. And sometimes we call them large ion lithophile elements also, another term for that, right? Remember this one also. So this one is called large ion lithophile elements, LILE, right? This low field strength elements. So elements here, cesium, rubidium, like these ones are low field strength elements. Okay, large ion lithophile elements, these ones. So these 4 comes as high field strength elements. Actually, there are several other elements also, high field strength elements, but basically we take these 4 because they are very much used in geochemistry. Okay. And there may be some other situations where you can have same charge and size. So this is the main important fact. It's not just whether they are lying close to each other in the periodic table. Do you remember? I mentioned that for elements which are lying close to each other in the periodic table, will behave similarly, right? So that is actually because of their size and charge. Because they are lying close to each other means they are having almost similar size as well as similar valency, right? Close valency. So the elements with the same charge and size, they are expected to show very similar geochemical behaviors. Okay. So, but obviously, these high field strength elements, they also they behave very similar manner, but actually their charges and sizes are different, as we just mentioned before, right? But normally the nearby elements like lanthanum, cerium, rubidium, strontium like elements, they have similar same charge and size, so therefore they behave similarly, and also they are sitting close to each other in the periodic table. So these are very important, very preliminary or fundamental aspects in lithogeochemistry. Considering the solid rock geochemistry, you have to always remember these fundamentals, because otherwise you will be in trouble when you are to interpret the composition of a given rock. Okay, so remember, although we predominantly talked about melts here, we are not only talking about, these are not only applicable to the melts, not only for the basalt. Any rock, any rock, you can apply these principles, because as long as they are behaving in a under a geological process. Even for metamorphic rocks, you can apply these ones. And of course, we do apply But the thing is, it has to be we have to be very careful when applying it into metamorphic systems, because during metamorphism there are a lot of changes to take place, right? Metallurgical changes are happening, but as a whole, or the system, we consider that they are for example, they are under the closed system behavior. Therefore, uh, no issue, we can apply, right? You can't see the screen. Is there any problem now? I can see a message. Okay, anyway, okay. Anyway, I hope you can see now. How we cancel means what? Okay, anyway. So just keep in mind these basic principles that we have to consider in solid rock geochemistry, lithogeochemistry, because these are very, very important when we are going to interpret a rock's geological processes, right? A rock's evolution. Okay, so do you have any questions? Do you have any questions to discuss? Any questions? No? Okay, so let me finish today. Then my probably this Zoom connection might be not working well also, because that's why you are not hearing very well probably, because in China Zoom is not allowed. I'm using a VPN. Okay, without VPN we can't use Zoom here. So they have other very nice what meeting softwares, Tencent or many other things, but which we are not using. So VPN might have some trouble. That's why you are connected and disconnected time to time. Anyway, we'll stop here for today. So we will continue from the next time. So always remember to go through more details on these keywords. So I gave you some keywords. So please try to read more on these keywords. Then you will be more comfortable with this course. Otherwise, I mean, when you always hear something you don't understand, it's very hard to proceed from there onwards. Okay, so the main words, I mean the keywords that we have been using during these lecture slides, you have to be very familiar. Okay, so if I say compatible elements, and this is incompatible, that is compatible, and this is high field strength, and that is ionic potential is that, these like that. So if you don't understand and if you can't remember, that is a problem. Okay, so therefore please try to read more. Okay, so we will